My name is Joshua. I welcome you to Coordination Learning Outcome C. Examine the properties and the functions of sensory receptors, the role of retina in visual perception, and the ear organs of balance in relation to their response to the environmental stimuli. We shall look at learning activities A, B, and C. In group learner search for discussion the type of sensory receptors and stimuli, delving into receptor properties. Shall look at the structure of the retina and the distribution of the photoreceptor cells, the ear's role in maintaining balance during position and movement. Let us start with the type of sensory receptors and the stimuli. Item 1. Your class is on a field trip. On the way, different students experience various sensations. Stella smells roasted maize from a roadside stall. Musa touches a cold metallic railing. Abby feels a sharp stone in her shoe. Peter sees a bright flash from a car headlight. Task. Identify the receptor types for each sensation. Smell. That was by Stella. It was olfactory chemical receptors were stimulated by chemicals in the air. Touch. Struck cold by Musa. Thermoreceptors and mechanoreceptors were stimulated by temperature changes and pressure. Pain, that was Abby. Nociceptors were stimulated by tissue damage and pressure, which was extreme. Vision, that was by Peter. Those are photoreceptors stimulated by light waves. We are still on the same item. Classify each receptor as exteroceptor or interoceptor. All listed receptors are exteroceptors because they respond to external stimuli. Interceptors would include baroreceptors, stretchceptors, carbon dioxide chemoreceptors in the blood vessels. Item 2. You place a coin on the skin of your forearm and leave it there for 1 minute. Describe what you feel over time. Initially, strong pressure is felt. After 20 to 30 seconds, the sensation fades due to receptor adaptation. Mechanoreceptors stop generating frequent impulses when the stimulus is constant. Adaptation decreases the sensitivity to a constant stimulus. Item 3. Students dip one hand in warm water and the other in cold water for 30 seconds. Then move both hands into room temperature water. Compare the sensation felt in each hand. The hand from warm water feels cold. The hand from cold water feels warm. Thermoreceptors respond specifically to changes in temperature, not absolute temperature. This demonstrates receptor specificity and relative sensitivity. Specificity: receptors respond best to one particular type of stimulus. Item 4. You pinch your arm lightly, then harder. Explain why only the harder pinch is painful. Lighter pinch activates mechanoreceptors, that is touch. Harder pinch activates nociceptors, which only fire when stimulus intensity crosses a threshold. Pain receptors do not adapt because pain is protective. Item 5. A patient reports that they could not taste food after a severe flu. They feel dizzy and off balance. They feel burning sensation in their feet at night. Task: identify the affected receptors and explain symptoms. They cannot taste food after a severe flu. Loss of taste. The affected receptors are the gustatory chemoreceptors of the tongue. Inflamed nozzle and oral mucosa may block access to chemical stimuli. They feel dizzy and off balance. Dizziness: the affected receptors are the mechanoreceptors in the inner ear, that is the vestibular. Disrupted fluid balance affects equilibrium detection. They feel burning sensation in their feet at night. The burning feet sensation, the affected receptors are the nociceptors or the pain receptors. Might indicate nerve irritation or neuropathy. Item 6. Farmers report the following when working. Eyes water when cutting onions. Skins feel hot after working in sunlight. Feels vibration from tractor seats. Identify receptors and stimulus involved. Eyes water when cutting onions. Onion irritation. These are chemoreceptors stimulated by volatile sulfur compounds. skin feels hot after working in sunlight. Heat from the sun, this one affects the thermoreceptor and photoreceptors. Ultraviolet radiation triggers both. Feel vibration from the tractor seat. Vibration activates the mechanoreceptors, Pacinium capsules. Let us now look at the summary of receptor types and stimuli. Summary of receptor types and stimuli. We have the receptor types, the stimulus detected, and we can give examples. Mechanoreceptors. The stimulus is pressure, touch, vibration. Example, Pacinium capsules. Thermoreceptors. The stimulus is hot or cold. An example, we have the skin receptors. Chemoreceptors. We have the stimulus as chemicals. Example, the taste, smell, and carbon dioxide. An example can be the taste buds, carotid body. We have the photoreceptors. The stimulus is light. Examples, we have the rods and the cones. Nociceptors. Stimulus is pain, tissue damage. Examples, the free nerve endings. And then we have the proprioceptors. This one, the stimulus is the body position. And the example, they are the muscle spindles. Let's look at the retina and the photoreceptor cells. Item 1. Your class is dissecting a cow's eye to observe structures similar to the human eye. When the teacher opens the eye, you see a shiny layer at the back, tapetum lucidum, the retina beneath it, and a yellow spot. Task. Identify key retinal structures visible in the dissection. Retina. This is a thin, delicate, light-sensitive layer lining the inside of the eye. The optic nerve. They are thick bundle where retinal ganglion cells converge and exit. Macular region, yellowish area. This contains high density of cones. The blind spot, a point where optic nerve exits. There are no photoreceptors. Item 2. Retina, the thin, delicate, light-sensitive layer lining the inside of the eye. Macular region, the yellowish area, contains high density of cones. Blind spot, a point where optic nerve exits. No photoreceptors. Task. Relate observed features to photoreceptor distribution. Retina, a thin, delicate, light-sensitive layer lining the inside of the eye. The peripheral retina contain mostly rods. which support dim light and motion detection. Macular region, the yellowish area, which contains high density of cones. The central region, which is the macula of fovea, contains mostly cones, which supports detailed color vision. The blind spot, a point where optic nerve exists, no photoreceptors. The blind spot has no rods or cones, so no image is detected there. Item 3. The teacher takes students to a dimly lit room and shows a colored picture. Students struggle to see the colors clearly. When the lights are turned on, the colors appear vivid. Task: explain why color vision was poor in dim light. In dim light, rods are active, but cones are inactive. Rods detect shapes and movement, but cannot detect color. Cones need bright light to function. Item 4. The peripheral retina contains mostly rods which support dim light and motion detection. Task: explain the advantage of rods in the peripheral retina. Rods are numerous in the peripheral, which detects movement and low light. This helps detect threats or motion outside direct line of sight. Useful for night vision and detecting predators. Item 5. Students sit in front of a periodic table chart and try reading letters in normal room light. They then try the same activity in dim light. Task: describe the role of fovea, central vision, during the test. The fovea has the highest density of cones. It gives sharpest visual acuity, allowing detailed reading. Without proper lighting, cones cannot function well, hence reading becomes harder. Explain why peripheral letters are harder to read. Peripheral retina has fewer cones and more rods. It is designed for movement detection, not fine detail. Therefore, peripheral vision is blurred and has poor color detection. Item 6. While walking home at night, a student notes that they see a distant car better when looking slightly away from it rather than directly at it. Explain this phenomenon. Looking slightly away uses peripheral retina, which is rich in rods. Rods are more sensitive to low light than cones in the fovea. Thus, faint light sources are detected better. Connect this to retinal structure. The fovea, the center of the retina, has only cones, which need bright light. Peripheral retina has mostly rods, which work well in dim light. This distribution leads to the better night vision of center. Item 7. A patient complains they cannot see well at night. Colors appear faded. They have difficulty reading fine prints. Task: identify what part of the retina is directly damaged. They cannot see well at night. Night blindness is as a result of rod degeneration. For example, retinitis pigmentosa. Color appear faded. Color fading is due to cone damage. They have difficulty reading the fine print. Poor reading is due to foveal cone damage or macular degeneration. The patient complains they cannot see well at night. Color appears faded. They have difficult reading fine print. Link the symptoms to photoreceptor distribution. They cannot see well at night. Rods are located in the periphery. Thus, night vision problems. Color appears faded. Cone concentrated in the fovea. Hence, color and sharp vision is affected. They have difficulty reading fine prints. Damage of the retina peripheral and the fovea explain the difficulty of reading fine prints. Let's now have a quick summary for students. Retinal structure. The retina, this is a layer of photoreceptors plus neurons that detect light. The fovea is the center where only cones and have the sharpest vision. Macula area around fovea with many cones. Blind spot, no rods or cones, only optic nerves exist. Photoreceptor distribution. The location, the rods, the cones, and the function. The fovea has no rods, very high cones, and it is for color and detail. Macula, very low rods, high cones, color, clear vision. Peripheral retina, very high rods, low cones, dim light and motion. The blind spot, no rods, no cones, and has no function. The ear's role in balance and movement. Item 1. Your class performs an experiment where a student sits on a spinning chair. Another student spins them gently for 15 seconds, then suddenly stops the chair. Task. Describe what the student feels immediately after the chair stops. The student feels dizzy or as if the room is still moving. This is because fluid in the semicircular canal continues moving even after the body stops. The hair cells in the canal bend due to the moving endoleaf, sending signals that the head is still rotating. Item 2. When a student sits on a spinning chair is suddenly stopped, the student feels dizzy or as if the room is still moving. Explain the ear structure responsible for this sensation. The semicircular canals detect rotational movement, dynamic equilibrium. Each canal is positioned at a right angle to detect motion in 3 dimensions. Movement of the endoleaf bends the hair cells in the crista, generating nerve impulse to the brain. Explain why dizziness fades after a short while. The endoleaf eventually stops moving. Hair cells return to their normal position, stopping false signal of rotation. The brain reestablishes correct orientation. Item 3. Students try standing on one leg with the eyes open, then repeats with the eyes closed. Describe what happens when eyes are closed. It becomes harder to maintain balance. Without visual cue, the body relies more on the vestibular apparatus, the atrial and sacral, and proprioceptors. Item 4. Without visual cue, the body relies more on the vestibular canal, atrial and sacral, and proprioceptors. Explain the role of atrial and sacral. This structure contains otolith, a calcium carbonate crystal that sits on a gel layer. When the head tilts or the body changes position, the otolith shifts. This movement bends the hair cells in the macula, signaling the brain about head position. This helps maintain static equilibrium, balance when not moving. Item 5. Still a student standing on one leg with eyes open maintains balance easily than when eyes are closed. Explain how the brain integrates information to maintain posture. The brain combines inputs from the vestibular system, the atrial, sacral, and the canals, the eyes, and proprioceptors in the muscle or joints. Integration helps maintain balance when one system is less active. For example, eyes closed. Item 6. While riding in a car, a student feels their body move forward when the car stops suddenly and feels pushed back during acceleration. Explain why the student feels these forces. Inertia causes the body to resist change in motion. The otolith organ in the atrial and sacral detect the linear acceleration. Item 6. While riding in the car, a student feels their body move forward when the car stops suddenly and feel pushed back during acceleration. Describe how the ear detects linear acceleration. When the car accelerates or stops, otolith shift in the gelatinous layer. This bends hair cells in the macula. The brain interprets this as forward or backward motion. When a car accelerates and stops, otolith shifts in the gelatinous layer. This bends hair cells in the macula. The brain interprets this as a forward or backward motion. Relate this to maintaining balance. The signals help the brain adjust posture, preventing falls. For example, when a car stops abruptly, you lean forward or brace to keep balance. Item 7. The school invites a circus performer who demonstrates walking on a narrow beam. Explain how the ear helps the performer maintain balance. The vestibular apparatus continuously monitors head position. Atrial and circular detect tilt. Semicircular canal detect movement. Signals are sent to the cerebellum to coordinate muscle adjustment. Predict what would happen if the semicircular canals were damaged. The performer would struggle with balance during movement. They might experience dizziness or vertigo. Coordinated motion, turns, steps, quick corrections become difficult. Explain why trained performers have better balance. Their brain practices integrating vestibular, visual, and muscular input more efficiently. This leads to faster reflex and better coordination. Item 9. A student plays a VR game where their eyes perceive fast movement, but their body is stationary. They soon feel dizzy and nauseated. Explain why motion sickness occurs. Visual system reports movement. Vestibular system reports no movement. The mismatch confuses the brain and producing nausea and dizziness. Identify which part of the ear is responsible. The semicircular canal and otolith organs detect no motion, but the eyes are sending conflicting information. Suggest a way to reduce motion sickness. To breaks or take breaks to rest the vestibular system, or focus on a stable object. They can use controlled or slow head movements, or there can be improvement on the frame rate in the VR to reduce sensory mismatch. Let's now look at the summary of the ear structures involved in balance. Summary of ear structures involved in balance. We have the semicircular canal. These detect rotational movement, that is dynamic movement. Crystal hair cells detect fluid movement in the canals. Atrial circular otolith organ detect linear acceleration or head tilt. This is static equilibrium. Otolith add weight to the gelatinous layer to enhance detection. The vestibular nerve sends balance information to the brain, and the cerebellum integrates balance signals for coordination. Thank you for participating in Coordination Learning Outcome C. Examine the properties and functions of sensory receptors, the role of the retina in visual perception, and the ear's organ of balance in relation to their response to environmental stimuli. We have been looking to learn activity A, B, and C. In group learner search for and discuss the types of sensory receptors and the stimuli, delving into receptor properties, the structure of the retina and the distribution of photoreceptor cells, the ear's role in maintaining balance during position and movement. Thank you. If it has been helpful to you, visit me at Mugabi Joshua Biology on YouTube.